we know that if we leave water to its own devices, so you have some H2O, that it's in equilibrium with the auto-ionized version of itself. So a little bit of it will turn into some hydrogen ions, and we know that this really takes the form of hydronium, that these attach themselves to other water molecules, and it could be H3O, but we'll just write it as a hydrogen ion right there, which is really just a free-floating proton, plus some hydroxide ion. And we also know that in kind of an equilibrium state at 25 degrees Celsius, and remember, equilibrium constants and equilibrium reactions only dependent on the temperature, nothing else. You don't, well, for a given molecule, of course. So at 25 degrees Celsius, we also know, and we did this 2 videos ago, that the equilibrium constant, and we could just, as a review, that's the concentration of the products divided by the concentration of the reactants, but the reactants in this case is just water. It's the actual solvent. And if the reactant is what it's everywhere. So if you just go back to that intuition example, the probability of finding it is 1 in any, so it's just always there. So you don't include it. So you could just say divided by 1 or whatever, and that this is equal to the equilibrium constant of water, and we learned that that's 10 to the minus 14, because water by itself will have a hydrogen concentration of 10 to the minus 7 and a hydroxide concentration of 10 to the minus 7. And if you take a log of everything, so if you take the pKw, what was that? Well, if you put a p in front of something, that means you're taking the negative log of it. So the negative log of 10 to the minus 14, the log base 10 of 10 to the minus 14 is minus 14. So the negative log is just 14. So pKw is 14, and that is equal to, well, if I take the negative log of this side right here? Let me do that. This is just a logarithm properties. This is more math than chemistry. So the log of H plus times OH times our hydroxide ion, that's the same thing, just logarithm properties. This is the same thing as minus log of H plus minus, or you could say plus, the minus log of OH minus. And what is this? Well, this is just the pH, which is equal to the minus log. This is 10 to the minus 7, right? 10 to the minus 7, the log of that is minus 7. You have the minus in front, so this pH is equal to 7. And what is this? This over here, this is our POH, the minus log of the hydroxide concentration. And of course, that was also 10 to the minus 7. And so our POH is equal to, the log of that is minus 7. You have a minus in front. It's equal to 7. So you get there, right? You get right there that little formula that the pKw, or the negative log of the equilibrium constant of water, pKw is equal to the pH of water plus the pOH of water. And this at 25 degrees Celsius, this is the thing that's going to stay constant, because we're going to start messing with these things by throwing acid and base into the water. This thing is always going to be 14 at 25 degrees Celsius. Remember, as long as you keep temperature constant and you're not messing too much with the molecule itself, your equilibrium constant stays constant. That's why it's called a constant. So with all of that out of the way, let's think about what happens if I throw some acid into a, let's say I have some hydrochloric acid. I'll use colors more creatively. So I have some hydrochloric acid. It's in an aqueous solution. We know that it dissociates completely. Which means that we're just left with, let me not do it like that. We're left with the hydrogen ion, which of course really attaches itself to another water molecule and becomes hydronium, plus the chlorine anion, or negative ion, right there. And let's say that let's say that my let's say I do this with 1 mole, 1 molar, 1 molar, or this is also sometimes written as 1 capital M, of hydrochloric acid. So essentially, what am I doing? I am taking 1 molar of hydrochloric acid. Literally means that I am taking 1 mole of HCl per liter of our whole solution, which is mainly water. It's an aqueous solution, per liter of water, right? So what's my concentration going to be of these things right here? Or in particular, what's the concentration of the H going to be? Well, if this disassociated completely, right? So all of this stuff, this is not an equilibrium reaction. Remember, I only do a one-way arrow to the right. There's no even small leftwards arrow. This is a strong acid, hydrochloric acid. So if you really put 1 molar of this in an aqueous solution, you're not going to see any of this. You're going to just see this. So you're going to have, so the hydrogen concentration here, in the aqueous solution is going to be equal to 1 molar. And there's also going to be 1 molar of chloride anions, but we don't care about that. We want to figure out, well, if I haven't said it already, it would be nice to figure out what the pH of this solution is now that I've thrown hydrochloric acid in it. Well, the pH is just a hydrogen concentration. So, well, we already have the hydrogen concentration. That's 1 molar, or 1 mole per liter of solution. So the pH is going to be equal to the minus log base 10 of our hydrogen concentration of 1, which is equal, 10 to the what power is equal to 1? Well, anything to the 0th power is equal to 1, including 10. So this is equal to 0. Minus 0 is just 0. So your pH is 0. So if you have 1 molar of hydrochloric acid, and you throw it into an aqueous solution, and well, I guess I'm saying you're putting it into a solution when I tell you it's 1 molar. So if you have a concentration of 1 mole per liter of solution, where the solvent is water, you will end up with a pH of 0. A pH of 0. What was water's neutral? So pH of water, just without any acid in it, that was equal to 7, and this is considered a neutral pH. Now we know that if you were to have a solution, an aqueous solution, with 1 molar of hydrochloric acid, we can say, I'll do it in red because it's pH of HCl in water is equal to 0. So obviously, a low pH is more acidic, and we went over that in previous videos. And let's figure out what the pOH of hydrochloric acid is. pOH of hydrochloric acid in an aqueous solution. Well, this all goes back to Le Chatelier's principle, right? If you go back to what we said before, this is just pure water right here. If we put 1 molar of hydrochloric acid in here, we're essentially just throwing a ton. We're just throwing a ton of hydrogen protons in there. We're substantially increasing the concentration of this. And Le Chatelier's principle says, oh, well, that means that a lot of this is going to be consumed and the reaction will go in this direction. The equilibrium reaction will go in that direction. But remember, water by itself only had a 10 to the minus 7 concentration. We're throwing in a million that's one. It was 1/10,000,000th of a mole per liter. Now we're throwing in one. What is that? We're throwing in 10 to the 7th. We're throwing in 10 million times as much hydrogen ions into that water. So all of this stuff just gets consumed. Maybe it goes there, and so the concentration of this gets thrown down really far because we're dumping so much, and the concentration of this goes up because it can only consume so much of these guys. There's not that much of this. There's only 10 to the minus 7th molar of this. So this ends up being 1 molar, and if this ends up being 1 molar, because that 10 to the minus 7th molar, essentially, you can kind of view it all gets consumed with this stuff over here. What ends up being the concentration of the OH? Well, we already know that the pKw is 14 of water at 25 degrees. And the pKw of water is equal to the pH of your solution plus your pOH. So if your pH is for hydrochloric acid is 0, right? We have 1 molar of hydrochloric acid. Then your pOH of 1 molar of hydrochloric acid is 14. So right here, our pOH is equal to 14. Now let's do the same thing with a base and figure out what its pH, a strong base. And I think you'll see that it's the opposite. So let's say I had potassium hydroxide. It's a strong base, so it completely disassociates in water to potassium cations, positive charged ions, plus hydroxide anions. It completely dissociates. So if I put, and it's in an aqueous solution, I should write that down. Aqueous solution. Aqueous solution just means we are in water, of course. And if we essentially put 1 molar, remember the concentration matters. You can't just say, oh, hydrochloric acid has a pH of 0. No, you have to say 1 molar of hydrochloric acid has a pH of 0. And actually, I didn't write that. Let me write that. 1 molar. 1 molar. And I'll leave you to figure out what the pH or the pOH of 2 molars of hydrochloric acid is, or of 10 molar of hydrochloric acid, and figure out what those pHs are. But if we have 1 molar, so we have 1 molar of potassium hydroxide. We have 1 molar of this. And it completely disassociates when it's in water, so you have none of this left over. Then what's your concentration of OH? Well, your OH concentration is going to be 1 molar. Right? If you had 1 mole per liter of this, you're going to have 1 mole per liter of this, because all of this just disappears in the water. So what is your pOH? pOH is just the negative log of this. The log of 1 is 0. The negative of 0 is 0. And then your pH in this circumstance, well, you could say, oh, well, it was the hydrogen concentration. Oh, you don't know what the hydrogen concentration is, but you know that when you throw a bunch of this stuff, it's going to sop up a bunch of hydrogen. The hydrogen is going to go down a lot. But you're like, well, how do I measure it? Well, you remember at 25 degrees Celsius, the equilibrium constant of water is equal to the pH plus the pOH. We showed that at the beginning of the video. So 14 is equal to your pH plus 0. That's our pOH in this case. So our pH is 14. So if you have 1 molar of, I use potassium hydroxide in this case, but if you have 1 molar of a strong base, let me write that down. 1 molar of strong base. Strong base. Remember, strong is a kind of an official term in chemistry. It means complete dissociation. You have a pH of 14, and you have a pOH of 0. If you have 1 molar of strong acid, if someone says that they have something with a pH of 0 that they would like to maybe throw at you, you should decline, because it'll probably hurt your chances of, well, anyway. So let's say you have 1 molar strong acid. It's a pH of 0 and a pOH of 14. And anyway, maybe in the next video I'll actually show you what this might give you the impression that this is an absolute scale, that 0 is as acidic you can get and 14 is as basic you can get when you get to pH. But that's not the case. You can actually get above this or you can get below this. This was just when you had 1 molar of a strong acid. If you had 2 molars of a strong acid, or actually if you had 10 molars, right? Let's say you get your hydrogen concentration to 10 molar. So then what's going to be your, so if you had 10 molar of a strong acid, you apply that in an aqueous solution. It is when I say it's molar by definition. What's your pH going to be? Your pH is going to be the minus log base 10 of 10. This is the log base 10 of 10 is 1. 10 to the first power is 1. So this is equal to minus 1. So minus 1 pH would if you had 10 molar of, say, hydrochloric acid or nitric acid or anything like that. Anyway, that's all for this video. I'll see you in the next one. In the last video, we learned that if I had some, let's say I have some weak acid, so it's hydrogen plus the rest of whatever the molecule is called, we'll just call it A. And I think this tends to be the standard convention for the rest of the acid, that it can disassociate, or it's in equilibrium because it's a weak acid. So it can be in equilibrium with, since it's a weak acid, it's going to produce some hydrogen proton, and then the rest of the molecule is going to keep the electrons. So it's going to be plus, all of this is in an aqueous solution. Let me do that. Aqueous. It's an aqueous solution. And then you're going to have the rest of the acid, whatever it might be, A minus, and that's also going to be an aqueous solution. And that's the general pattern. We've seen the case where A is, A could be equal to, it could be an NH3, right? If A is an NH3, then when you have this, you have an NH4 plus, so this would be ammonia, and this is just NH3. A could be just it could be a fluorine. It could be a fluorine molecule right there, because then this would be hydrogen fluoride or hydrofluoric acid, and this would just be the minus the negative ion of fluorine, with an extra electron. So it could be a bunch of stuff. We've done it could be, you could just throw in anything there and it'll work, especially for the weak acid. So we learned in the last video that if this is the acid, so if this is the acid, then this is the conjugate base. Conjugate base. And we could write the same reaction essentially as kind of more of a basic reaction. So we could say, if I start with A minus, it's in an aqueous solution, that's in equilibrium with, this thing could grab a hydrogen from the surrounding water and become neutral then. It's still in an aqueous solution. And then one of those water molecules that it plucked that hydrogen off of is now going to be a hydroxide molecule. Right? Because this hydrogen, remember, whenever I say pluck the hydrogen, just the proton, not the electron for the hydrogen. So the electron stays on that water molecule, so it has a negative charge. It's in an aqueous solution. So we could write the same reaction both ways. And we can write equilibrium constants for both of these reactions. So let's do that. Let me erase this just because I can erase this stuff right there. I'm going to use that space. So an equilibrium reaction for this first one, I could call this the K sub A, because the equilibrium reaction for an acid. And so this is going to be equal to its products. So the concentration of my hydrogen times my concentration of whatever my conjugate base was, divided by my concentration of my original acid, my weak acid. So this would be the concentration of HA. Fair enough. I could also write an equilibrium constant for this basic reaction. Let me do it right down here. So I'll call that my K sub B, for this is a base equilibrium. And so this is equal to the concentration of the products. Becoming tedious to keep switching colors. Actually, I'll do it because it makes it easier to look at least for me. HA times the concentration of my hydroxide ions divided by my concentration of my weak base, A minus. Remember, this can only be true of a weak base or weak acid. If we were dealing with a strong acid or a strong base, this would not be an equilibrium reaction. It would only go in one direction. And when it only goes in one direction, writing this type of equilibrium reaction makes no sense, or equilibrium constant, because it's not an equilibrium. It only goes in one direction. If A was chlorine, if this was hydrochloric acid, you couldn't do this. You would just say, look, if you have a mole of this, you're just dumping a mole of hydrogen protons in that solution and then a bunch of chlorine anions who are not going to do anything. Even though they are the conjugate base, they wouldn't do anything. So you can only do this, remember, for weak acids and bases. So with that said, let's see if we can find a relationship between Ka and Kb. So let's divide. Let's see, what do we have here? We have an A minus on both sides of this. So maybe we have H over OH over A minus. Let's see, if we divide both, let's solve for A minus, right? If we multiply both sides of this equation by HA over H plus, we get, on the left-hand side, we get Ka times the inverse of this. So you have your HA over H plus is equal to your concentration of your conjugate base, A minus. And let's do the same thing here, solve for A minus. So to solve for A minus here, we might have to do two steps. So if we take the inverse of both sides, you get 1 over KB is equal to, I'll just stick to, well, A minus over, let me go down a little bit lower, over H, the concentration of my conjugate acid, times the concentration of hydroxide. Multiply both sides by this, and I get A minus is equal to my concentration of my conjugate acid times concentration of hydroxide, all of that over my base equilibrium constant. Now, these are the same reactions, right? In either reaction for given concentrations, I'm going to end up with the same concentration. This is going to equal that, right? These are two different ways of writing the exact same reaction. So let's set them equal to each other. So let me copy and paste it, actually. So I'm saying that this thing, copy, this thing is equal to this thing right here. So this is equal to, let me copy and paste this, that. That's equal to that. So let's see if we can find a relationship between Ka and Kb. Let's see if we, well, one thing we can do, we can divide both sides by HA, right? So if we divide both sides by HA, actually I could have probably done that earlier on in the whole thing. Yeah, well, anyway, I could have done that earlier on. But let's say if we ignore this part right here, this is equal to that. So we could write, let me erase all of this. Well, I'm using the wrong tool. So we could say that they both equal the concentration of A minus. So that's equal to that. We can divide both sides by HA. So if we divide, so this will cancel, this over here will cancel with this over here. And we're getting pretty close to a neat relationship. And so we get Ka over our hydrogen concentration, our hydrogen proton concentration, is equal to our hydroxide concentration divided by Kb. We can just cross multiply this. So we get Ka, our acidic equilibrium concentration, times Kb is equal to our hydrogen concentration times our hydroxide concentration. Remember, this is all in an aqueous solution. What do we know about this? What do we know about our hydrogen times our hydroxide concentration in an aqueous solution? We know, so we know that, for example, let me go review just to make sure I'm jogging your memory properly. We could have H2O. It can auto-ionize into H plus OH minus. And this has an equilibrium. K sub W, it's equal to, you just put the product, so the concentration of the hydrogen protons times the concentration of the hydroxide ions. And you don't divide by this because it's the solvent. And we already figured out what this was. If we have just completely neutral water, this is 10 to the minus 7, and this is 10 to the minus 7. So this is equal to 10 to the minus 14. Now, these two things could change. I could add more hydrogen, I could add more hydroxide, and everything we've talked about so far, that's what we've been doing. That's what acids and bases do. They either increase this or they increase that. But the fact that this is an equilibrium constant means that, look, I don't care what you do to this. At the end of the day, this will adjust for your new reality of hydrogen protons, and this will always be a constant as long as we're in an aqueous solution, a solution of water where water is the solvent, at 25 degrees. So we're always, so this, no matter what we do, I mean, in just pure water, it's 10 to the minus 7. But no matter what we do to this and this in an aqueous solution, the product is always going to be 10 to the minus 14th power. So that's the answer to this question. This is always going to be 10 to the minus 14 if you multiply hydrogen concentration times OH concentration. Now, they won't each be 10 to the minus 7 anymore because we're dealing with a weak acid or a weak base, so that they're actually going to change these things. But when you multiply them, you're still going to get 10 to the minus 14. And then if you take, well, let's just take the minus log of both sides of that. Let me erase all of this stuff I did down here. I'll need the space. So let's say we take the minus logs of both sides of this equation. So you get the minus, let me do a different color, minus log, of course it's base 10 of Ka, let me do it in the colors, Ka times Kb is going to be equal to the minus log of this, is equal to the minus log of 10 to the minus 14. So what is this equal to? The log of 10 to the minus 14 is minus 14, because 10 to the minus 14th power is equal to 10 to the minus 14. You take the negative of that, so this becomes 14. So the right-hand side of your equation just becomes 14. And this one, we could use log properties. This is the same thing as the minus log of Ka. Let me use the colors. Ka plus the minus log of Kb. Or, though you could think of this, this is your pKa, this is your pKb. So you could say this is pKa plus pKb. Oh, I wanted to use blue. Plus pKb, and all of that's going to be equal to 14. Now, why is this useful? Well, if you know the pKa for a weak acid, for example, like let's say we have NH4 plus. This is a weak acid, right? It can donate an H, but it's not an irreversible reaction. That H can be gained back. So this is a weak acid. If you look it up on Wikipedia, you'll see it'll tell you. It'll say, hey, it's the pKa of NH4 is equal to 9.25, right? So this is 9.25 for NH4, for ammonium. So what is going to be the pKb for ammonia, right? Let me write that reaction down. We could write, so this is NH4 is in equilibrium. This is plus. It can get rid of one of its hydrogen protons, and you're just left with ammonia. Or you could, so this is the acidic reaction. So this is what the pKa is associated with. So the equilibrium constant for this reaction is the negative log of the equilibrium constant is equal to 9.25. And if I had the reverse reaction, the conjugate base reaction, so ammonia converts to ammonium plus it grabbed that hydrogen from a water molecule, that hydrogen proton from a water molecule. If I wanted to figure out the pKb, or the equilibrium constant, or the negative log of the equilibrium constant for this reaction, what is it? Well, this one's 9.25. And 9.25 plus this pKb have to be equal to 14. So what's 14 minus 9.25? It's what? 4.75. So we immediately know the equilibrium constant for the conjugate base reaction. So it's a useful thing to know that the pKa plus the pKb is equal to 14. And always remember, you see these pKa, pKb, and you say, what is that? Well, if you see a p, it's a negative log of something. And in this case, it's a negative log of the equilibrium constant for an acidic reaction, plus the negative log of the equilibrium basic reaction, where this is the conjugate base of this acid. It's always going to be equal to 14 if we're dealing with an aqueous solution at 25 degrees Celsius, which is essentially room temperature, which is usually going to be the case.